Welcome to the N1IR Electronics blog, video number 6, TDA, RDF, what the? Okay, basically, what I'm going to describe is some basic direction finding using time difference of arrival signal. I was approached by a couple hams and how to describe this, and basically here is a basic circuit for time difference of arrival. This circuit is similar to what the Ltronics little Elper is, and there's tons of designs that are very similar to this. Basically, you have four elements. You have your what I call hot element and a ground element. These are quarter wavelength for whatever frequency you're trying to receive, and also there's a coax here that has to also be quarter wavelength. Same for on the other side. You have a quarter wavelength hot antenna and a quarter wavelength ground. Same thing with the coax. Now these two assemblies have to be exactly symmetrical. If they're off like an inch or 2 inches, you'll get some differences. And we'll go into how this whole circuit works in a minute and why that's important. But basically it's a very simple construction. You have two resistors. These are just current limit resistors for these two diodes. These two diodes are typically, I like to use pin diodes for these, but you can use 1N4148s or 1N34 germanium, and I've even seen 1N4001s being used. So it's not too critical on these diodes and what you can use. I would suggest definitely with pin diodes if you have access to them. If not, a 1N4148 will do just nicely. Okay, so we have a couple diodes here. So we have our hot lead coming in through our coax. It gets terminated by this 470 ohm, and we have a couple diodes. We go down here. We have a capacitor. This is a coupling cap, so it blocks DC. That could be anything. It's not too critical on the value. I chose 1000 picofarad, but any value in the picofarad range would do fine. It all depends on frequency, what frequency you're trying to receive. This is for 2 meter that I have set up here. Right here is our BNC coax connector going to our radio. The coax here can be any length connecting to your radio. It doesn't really matter. It's not too critical on that. And over here we have our battery. This is not critical either. Anything above like 3 volts, 9 volt, that's fine. So you could stick a 9 volt battery in here and have a really long life. Right here is our 1 kilohertz oscillator. Now that's up to you what you can do with an oscillator. You can use a LM555, a TLC551 as an oscillator, or a CMOS gate as an oscillator. Doesn't really matter. As long as you can go from anywhere from like 500 hertz to a kilohertz. I have mine set up to a kilohertz. And that's going to be the frequency at which these two diodes will switch back and forth. It's not too critical on what frequency. It's whatever pleasant to the ear, like what you want to listen to. You want to listen to a 500 hertz signal a little bit lower, or you want to hear a high pitched noise. So basically, what this does is you have the oscillator, and we have our switch. In this position, this is what's called our DF mode, direction finding mode. And basically, what happens is that these two diodes get switched on and off, back and forth, sequentially, depending on the oscillator frequency. So it goes back, forth, back, forth, back, forth. And the interesting thing is, when you receive a radio signal, if both of these antennas are facing the direction of the transmitter and equally getting the same amount of voltage, the impedance of these two diodes are going to be the same, and they're going to pass the signal through this 470 ohm to ground, and you won't hear anything coming out of the receiver. You'll hear what's called a null signal. However, if this or the other antenna is different in strength, if one is greater than the other, you'll hear a tone. And that's because the impedance of these two guys are going to be different. This is basically operating as what's called an analog OR gate. And it doesn't, it's doesn't, it's not really too frequency dependent on this, so it's actually the receiver itself is being, is discriminating the signal. When you have this type of setup, really the bandwidth is determined by these quarter wavelengths, so it'll get you kind of within the 2 meter band or whatever band you're working on. But it's every signal on that band, so really it's the receiver that's doing all the work on filtering out. These two are just doing all the frequencies coming in. It's pretty interesting how it works. So basically, if I have, this is the top view, I have an element here, and I have an element here, and here's our boom. So this is viewing from the top. I have another element on the bottom, which is your ground. And if I have a little transmitter here, right now, these two are going to be the same voltage coming in. They're going to be the same signal strength. So you're going to hear a null. Now, when you move the transmitter to, say, like over here, this one has a longer distance to travel, so it's going to be a weaker signal. This one has a shorter distance, it's going to be a stronger signal. You'll hear a tone. And that works all well and good. You can receive and have a bearing on your signal. However, if you have a transmitter here, let's move our transmitter here, you'll have the same thing going on in the back of you. So forward direction and backwards direction can't really be handled with this circuit unless, here's the nice thing about this, this can also turn into a Yagi configuration. A lot of other circuits don't do this, but the little Elper does by Electronics. And what they do is they have a little switch up here. It has DF mode, and then they have a switch, it's called receive mode. When you throw that switch to receive mode, it takes it off DF, takes that oscillator out, and look what happens. Now, this diode turns on, and basically what that does is it grounds out this element. So now this is considered ground, this is ground, and we have our receiving element here. So now it turns it into a little Yagi antenna. And that's how you can determine, go back to this, what direction the transmitter is at. So you can find it this way, then you can switch it to Yagi mode, and when you switch it to Yagi mode, now the direction of travel is this. So when you have your transmitter here, you'll have a maximum signal strength. When you have your transmitter back here, they'll have very little signal strength. And that's pretty interesting. Basically, you can do the two modes with just one little switch and a battery. And basically, that's how this thing works. And I'm going to stop the video. I'm going to do part 2 on basically ELTs and what they look like and how you can receive them and stuff like that. So this made me, I've been talking about the little Elper. Here is a picture of it. And all this is a crystal receiver. There's nothing really, and you have a sensitivity adjust. You can do this with a resistor decade box as well, in line with the handheld. Or you can switch off frequency, which is another little trick I'll show you in the next video. So here you go, off, receive, DF. So when you're in receive mode, it shoots up that voltage and turns on that dot and turns it into a Yagi. When you're in DF mode, it has that oscillator in there, and if there's a difference in impedance on those two diodes, it'll have a null or it'll have a tone, and that tone's determined by your oscillator here. So like me, I can't really hear low frequencies, so I like to crank it up to a kilohertz. It's real easy to hear. It's right at the center human hearing. And that's basically how this thing works. It's a pretty neat circuit, very inexpensive to make. You can get all the parts at Radio Shack. The elements, I've seen them made out of coat hanger. I've seen them made out of tape measure. I make mine out of stainless steel, some stainless steel rod. The coax RG58 or even RG174. And this should all be enclosed in a metal box. And you can also do a quarter wave, or even I've seen even an eighth wave elements in coax, and that reduces your sensitivity even more. So that's it. Hope you liked the video.